Hello, everyone. Thanks for joining me today. My name is Hossam Barakat. I work as a senior consultant with Redify. This is my Twitter handle and my plug if you'd like to follow me. Today, we're going to talk about Kubernetes. And our agenda for today would be talking about what is Kubernetes and why we should care about it. And then we will have a walkthrough of the Kubernetes architecture. And after that, we'll see how would we leverage the Kubernetes building blocks in order to deploy a typical ASP.NET application that communicates with a SQL Server database on top of it. So let's start with having a shared understanding about containers. But before we do that, how many of you have used containers already? Oh, wow, that's almost everyone. That's great. So historically, we used to deploy our applications on top of physical machines. And in order to make a better utilization of the hardware, we were deploying multiple applications on the same machine. And that meant that the applications, as well as their dependencies, were entangled with each other, as well as with the host operating system, which didn't provide us with a good isolation between the applications. And that brought us into the virtual machines, which provided us with better isolations when we were using one application per virtual machine. But it was very heavyweight because it's hardware virtualization. And that led us into the containers technology. And the containers is basically providing us with a standard way to package the application, its dependencies, runtime, and configurations in a standard package. And then we could provide this package into a container engine. And that container engine could spin up multiple containers based on that package. Containers provided us with the same benefits that we had from with the virtual machines from isolation perspective. So containers cannot access each other. But it's more lightweight, so we can move the exact same package across different environments. And the reason behind that is containers is using operating system level virtualization. And there are multiple container engines in the market, but the most used one is Docker. And Docker is a platform that allows us to develop and run applications using the container technology. And thanks to the container technology, we could package any kind of application in a container, regardless of its language or runtime. So we could package applications written in Node, JavaScript, Go, ASP.NET, or any other language. And once we package our application, we could deploy this application into a production environment that has a Docker engine running on top of it. And if we are lucky, our application will start go viral, and a lot of users will start consuming it. But in a container-based environment, this will start bringing more challenges, such as how could we scale our application automatically to address the load that's coming to it? Or how would we have some sort of self-healing features so if the container died, we spin up another one to replace the one that just died? How could we have some sort of highly available environment so if the host that is hosting our containers died, we schedule those containers on another host in order to run the same containers? Our application might keep growing to a certain extent that we decide to split it into a set of microservices, which will start bringing more challenges, such as how would the services communicate with each other? We need to have some sort of service discovery between those services. And all those challenges in a container-based environment are usually resolved with using a container orchestration platform. And container orchestration platforms allows us to manage containers at scale. So there are a lot of features that comes out of the box with the container orchestration platforms, such as service discovery, scaling, horizontal health monitoring, failover, networking. And there are multiple container orchestration platforms available in the market. But the one that we're going to keep talking about today is Kubernetes. And Kubernetes is an open source container orchestration platform that allows us to automate the process of deploying, scaling, and managing containerized applications. And Kubernetes brings, in addition to the features that comes with any container orchestration platforms, more features such as self-healing, horizontal scaling of the nodes that are hosting our application and to our applications themselves or the containers. It also brings automated rollout and rollback, secret and configuration management, storage orchestration, and heaps of other features. So let me walk you through a very high-level overview of the Kubernetes architecture. Any Kubernetes cluster consists of two types of nodes. The first type of node is the master node, and the master node is the one responsible for managing your cluster. And this is the entry point to run anything on a Kubernetes cluster. And the worker node is actually where your container actually run. And let's assume we have packaged application and we wanted to deploy this container on top of Kubernetes. And let's see what are the key components that live inside our architecture or our nodes that gets involved in that. The entry point to any Kubernetes cluster is a component living on the master node called API server. And the responsibility of the API server is exposing set of APIs to be consumed by any client. And any client such as the Kubernetes CLI, which is kubectl, or the UI dashboard, or any other client that could make a call to those APIs. So one of those clients will send a request to the Kubernetes cluster to say, or to the API server, we would like to run that container on top of the cluster. The API server will validate the request, process it, and will save that request into a database. And that database is etcd database. And etcd is basically a distributed key value store that is used by Kubernetes to maintain its cluster state. Once we save the state into the database, another component comes into play, which is the scheduler. And the responsibility of the scheduler to find the best worker node to host your container. And it takes into consideration stuff like the hardware requirements for your container. And once it finds that node, it just updates the state in the database through the API server. Nothing has been scheduled yet. Then another component comes into play, which is the kubelet. And the kubelet is a component that runs on each worker node. And its responsibility is to keep watching the API server to find if there is any work to be scheduled on that worker. And it will find that there is a container to be scheduled. And at that point, it makes a call to another component living on the worker, which is the container runtime. And there are multiple container runtimes, such as Docker or Rocket, or there are other containers that satisfy the container runtime requirements. And the container runtime is the one that actually spin up your container. So at this point, those are the main components required to run your container. But there is one more key component that I would like to make sure that you are aware of on the Kubernetes cluster, which is the controller manager. And you can think of the controller manager as infinite loop that is running all the time. And the responsibility of the controller manager is to keep monitoring the cluster. And keep comparing the current state of the cluster versus the desired state of the cluster. So as an example, if we requested to run 2 instances of a certain container, and the controller manager found that the current number of the containers is 1, it will make some corrective actions to make the current number of containers to be 2. And those are the key components that everyone should be aware of while you are working with a Kubernetes architecture. Now that you know Kubernetes, you might be interested in trying this on your machine or on any other environment. And there are multiple ways to start working with Kubernetes. The first one is running it on a local host. And you could use Minikube or Docker for desktop. So if you already have Docker installed, there is one checkbox. Once you tick it, you will have a Kubernetes cluster running on your machine. You could run Kubernetes on premises, either on a virtual machine or a hardware physical machine. You could also use any of the cloud offerings that, such as Google, AWS, or Azure, which provides you with platform as a service offerings as well. And once you have a Kubernetes cluster, you could deploy your containerized application on top of it. So I'd like to spend the rest of the talk showing you how do we actually deploy a typical ASP.NET application communicating with a SQL Server database on top of it. Then how would we scale our application so we have multiple instances of the same application with a load balancer sitting on top of it to be used by the clients, and that application will be communicating with a highly available SQL Server database. So let me show you the application. And the purpose today is not to actually build the application, but we'll see how would we take the already built application onto the journey of running it on top of the cluster. So it's a typical tasks list application. It's built with ASP.NET Core. And it has like home, about, contact, and tasks. And tasks is basically having a CRUD operations for a task list. And I'm using Entity Framework Core to communicate with a SQL Server database. So I can add another task. And this is providing us with the typical like add, delete, mark as completed. So the first step in order to deploy our application on the cluster is to containerize this application, to build that package. Once we containerize it, we have to to configure it in a way or package it in a way that could be understood by Kubernetes cluster. And that is the pod. Pods are basically the atomic unit of scheduling inside Kubernetes. our application container will always live inside a pod. It will never be outside a pod. And the pod could contain multiple containers living inside of it. And those containers could communicate seamlessly because they share the same network namespace. In addition to that, the pod itself could have volumes. And volume is basically a data directory. And we'll talk about the details of the volumes later on. And that volume could be consumed by the containers living inside that pod. And pods usually represents a single instance of an application, which means if we would like to scale our application, we will deploy more pods as opposed to deploying more containers inside the same pod. So let's see how would we actually package our application, deploy it as a pod on top of Kubernetes. So here is our application in Visual Studio. It's a typical ASP.NET Core application. This is our tasks container. It's using Entity Framework context to communicate with the SQL Server database. So the first step, as I said, is to containerize it. And we could add a container support for our application or add a Docker file using the built-in feature of Visual Studio of add Docker support. And once you add Docker support, this will create a Docker file for you, or you could write a Docker file from scratch. So let me show you the Docker file. Everyone can see at the back? All good? So here's our Docker file. This is the one that just comes out of the box with the ASP.NET template. What we have here is basically the instructions to package our application. The first step is defining the port that this application will be receiving the requests on top of it. Then we have the first step is NuGet package restore. Then we are copying the rest of the application file. And the next step is building and publishing the application. And finally, we are defining what is the entry point of our application. So each time we run a container, this command will be the command that will get executed inside that container. Now we package it. Now we created our Docker file. The next step is to create an image. So this is just a plain text file. We didn't actually create the image so far. And in order to create an image, we can use a Docker command, Docker build, and provide the image name. And then we provide the build context, which is if our Docker file have any paths, it will depend on that context file, on the context that we provide. Once we do this, all the instructions that we have inside the Docker file will be executed, and it will provide us with an image. I have already done that, so we don't have to see the whole, wait for the whole build image to complete. So I have created a couple of images based on that application, and they are called Hossam Barakat /task list. As you can see, I have already built 2 images for our application. And those are the ones that we can use to deploy to our Kubernetes cluster. We can run that container on top, or that image on top of Kubernetes in 2 ways. The first one is the imperative way. And the imperative way is basically using the kubectl, which is the Kubernetes client, provide it with a command run. Then we provide the image name. And this will run a pod or run our container on top of the cluster. And the other way is the declarative way. And this is actually the one that we're going to use today. And the declarative way is basically building a YAML file or JSON file. And that YAML file, we could provide it into our kubectl. And the kubectl make the relative call to the API server inside the Kubernetes cluster. So let's see the YAML file of our pod definition. Generally, any Kubernetes object require 4 parameters. The first one is the kind of the object that we would like to create. Second one is the API version. And as I said, the key entry point to the cluster is the API server. And this is basically telling the kubectl which API version that we would like to talk to. And based on that version, the spec section, which is like the body of your request, could be different based on that version. We have another object, another attribute, which is the metadata. And in this case, we are just providing the name of the pod. Then the spec section. The spec section is like the body. For our pod, we could have multiple containers living inside of it. But in this case, we only have 1 container, which is the ASP.NET application. So we provide the container name. We provide the image that we have built. And the image pull policy, this is basically telling Kubernetes to use the image that I already have built or grabbed on my local machine And this is just to save a few moments in our demo. The last bit is the port that this container is exposing, and this is the same port that we have in our Docker file. With that object created, we can use kubectl and provide it with the command apply, provide the file, and we can see that there is a pod created. Kubernetes provides us with another key component, which is a Kubernetes dashboard, which is a GUI that allows us to explore the objects that have been deployed on top of Kubernetes. So if we switch to the Kubernetes dashboard, we can see there is a section for the pods. And we have our pod has been created already. And we can see the details of the containers living inside that pod. So our container will be the tasks app and the image that is used inside that container. And I can connect to my application to verify that it's actually running using a feature in Kubernetes, which is port forward. So I'll use kubectl port forward, provide the pod name and the host port and the port that I will be targeting. And this will build a tunnel between my host machine and the pod. Once we run that, I will open a new tab, and let's try. There you go. Our application is already running. So far, we managed to deploy our application as a pod on top of Kubernetes. But what happens if that pod dies for any reason? If the pod dies, Kubernetes will not automatically spin up another pod for us. It doesn't provide this self-healing feature out of the box for the pod. But we could leverage another object in Kubernetes, which is called ReplicaSet. And ReplicaSet is providing us with this feature to tell Kubernetes to maintain a certain number of replicas from a pod. And this means if the pod dies, another one will be spinned up automatically. And so if we assume that we have a scenario that we would like to maintain 2 instances of an Nginx container, in the first time when we deploy our ReplicaSet, Kubernetes will go and create 2 pods on the workers that we have. But if anything went wrong with any of the pods, like for a worker failure, Kubernetes will automatically discover that there is the number of the pods are less than the desired, and it will automatically spin up a new pod on one of the healthy nodes. And this is happening thanks to those like infinite loops that are running on the Kubernetes master. And the way the ReplicaSet connects to the pod is using another feature in Kubernetes, which is labels. And labels are providing us with a set of key values that could be assigned to a pod, a ReplicaSet, or any other object on Kubernetes. So we deploy our ReplicaSet to Kubernetes, telling it, please maintain a certain number of pods that have that label or multiple labels. So let's see how would we switch our pod to be controlled by a ReplicaSet and see those self-healing features in action. First of all, I will stop this. We'll clean this deployment so we can create our ReplicaSet. Here's the ReplicaSet object definition. Again, the same 4 parameters. The kind of the object is ReplicaSet, the API version. And as you can see, the version that we are using for the ReplicaSet is different from the version that we are using for the pod. And that's fine because each API could have its own different versions. And then the name of the ReplicaSet that we are using. Then the spec definition. And inside the spec, we have the number of replicas that we would like to maintain of that pod. Then we define the selector. This is where we define the label that we will be using to find out the pods. And in here, we are using match labels. We will try to find the pods with the label that has the key app and the value tasks app. The next part is template. And template is basically the pod definition, which is more or less what we had in the last file of the pod object definition. The only difference here is the labels section that we have added to the template section, which means any pod that will be scheduled based on that ReplicaSet will have that label. And this is the same label that we are using in the label selector for the ReplicaSet. So let's apply or deploy this ReplicaSet. Again, using the same command, kubectl apply, and we'll provide the file name. And this will create our ReplicaSet. Switching back to the dashboard, we can go and inspect the ReplicaSet section And we can see that our replica set has been created. And inside that replica set, we have 3 pods. And each pod is based on, it has the same container that we had in the last demo with the same image name that we have defined. The only difference is that label section, it has the label that we have added to the template definition. And if I grab this pod, I can connect to it using the same port forward, similar to the last time. We provide a different port, just to make sure that we are connecting to the right application. We need to change this port as well. And there you go. The application is running with the replica set, which is more or less what we had in the last demo. But the difference now is if we decided to go to the replica set, and if any of those pods dies, and I can do this by just actually deleting one of those pods, another one will be automatically scheduled for this replica set, because the Kubernetes cluster found that the number of pods is less than the desired, and it will automatically spin that new pod. And if I keep deleting, Kubernetes will keep creating another pod. And one of the good things with the replica set is we can scale the number of replicas that we are monitoring just with an ad hoc command from the kubectl, or using that scale in the dashboard. So right now, we're only having 3 pods. We could scale this to be 6 or 7 or any number that we would like to. So it's 6 or 7. This is going to create automatically the pods. And again, if any of those pods died, Kubernetes will automatically spin up another pod to replace it. So this is how would we deploy our pod and have some sort of self-healing using the replica set. But usually, after the first version is rolled out, we would like to deploy a new version of our application. And usually, we would like to do this with minimal downtime, and hopefully, we'll have some safety mechanism. So if something goes wrong with our deployment, which shouldn't happen, we would roll back to the old version of the application. And in order to get those kind of features, we need to use another object to control our replica set. And that object is the deployment object. And the deployment objects allows us to have those sort of rollout and rollback features for our replica set. So the first time we deploy our application, a replica set will be created with the pods living inside of it. But the key features with the deployment is if we decided to roll out a new version of our application, and this would usually happen by building a new image and providing the new image name to the deployment object. Behind the scene, Kubernetes will go and spin up a new replica set. And then it will start spinning up new pod inside the replica set using the new image. And then it will kill another pod in the old replica set. And it will keep doing this process till all the desired pods are created in the new replica set, and all the old pods are deleted from the old, or killed in the old replica set. And if something, at that point, the deployment will be pointing or monitoring the new replica set. And if something went wrong, so if we found a bug in the new release, we could easily roll back to the old replica set, and the same process that happened with the rollout will happen with the rollback. So let's see how would we use a deployment object in order to roll out a normal replica set. Then we will update it or roll out a new version of our application. Let me stop this and clean the deployment. Here is our object definition. Again, the kind is deployment, the API version that we are using, and the name of the deployment object. And the rest of this file is more or less it's exactly the same that we have in the replica set. There are other parameters that we could provide to the deployment object, such as the rollout strategy, which is basically controlling how many pods should be created while we are rolling out versus how many pods that should be killed in the old replica set. But for the sake of this demo, I'll keep it simple. I will not provide any extra parameters. And let's see how would we actually deploy this. Again, it's one command. It's kubectl apply, provide the file name. And this will create our deployment. Switching back to the dashboard, we can see that the deployment object has been created. And inside the deployment is a replica set. And inside the replica set are the pods. I would like to take a note of that replica set so we can compare. With the new replica set when we roll out a new version of our application. And again, if I connect it to any of those pods, we should be able to view the application running. So I'll use port forward, provide the pod name and different port again to make sure that we are, yes, I mean port forward. And change the port here. Here is our application running. Again, as you might have noticed, the tasks tab will not be working right now because we actually didn't deploy the SQL application yet, but we'll do this in a few minutes. So we have deployed our application, and we have seen the deployment object has been created. But right now, we would like to roll out a new version of that application. And we do this by changing the image name. So I have already created a new image, and that image has the tag v2 or the name v2. And when we roll out this version, our application should have v2 shown beside the tasks list. So let's update our deployment. I'll just call the same command. And then let's switch back to the dashboard to see what happened. Here's our deployment, and it's still running, and now it's done. A new replica set has been created, and we know this because we have taken a note of the old replica set, and as you can see, the name of the replica set is different from the old replica set. And the new replica set has new pods living inside of it, and those pods are based on the new image name that we have provided in our object definition. So if I connect it to that pod right now, I should be able to see the v2 happening in the home page. So yes, we would like to do port forward, but on a different pod. So if we refresh the home page right now, we should see v2, which is great. But the greatest thing is to see how this process happened behind the scene. And I'd like to show this using a command in Kubernetes called describe. And the describe command could be used with any object that we have in Kubernetes to see the details of that object. And as a part of that, we can see the events that happened on that object lifecycle. So let me clear that. kubectl describe. I'd like to know the details of the tasks app deployment. And this will show us the template definition of the pod, the containers that are living inside of it. And this is a rollout or rolling updated strategy, and we can change those parameters. But the section that I wanted to make sure that you see here is the events section. So when we first deployed our application, it created a new replica set, and that replica set is the one that we have taken a note of it here, and scaled this replica set to 3 immediately. But then we requested to roll out a new version of our application. And what happened is a new replica set was created, but it scaled only to 1. And then the old replica set was scaled to 2. And again, the new replica set scaled to 2, the old replica set scaled to 1. So this is the process of creating and killing the pods inside the replica set, till all the pods in the new replica set were created. So the desired replicas became 3, and the old replicas become 0. And we can see the revisions. So the more we do more deployments or updates to our deployment object, we can see all those revisions using a command called kubectl rollout history of a certain deployment. Sorry. As you can see right now, we have 2 revisions. The more we deploy, the more we have revisions. And with the deployment, we could roll back from the current revision to the old revision, and we can do this using the undo command. So let's do that. So I'll try to roll back from the current version to the old version. kubectl rollout undo deployment tasks app deployment. This is the deployment name. And right now, if we go to the dashboard, we can see that the deployment object is being updated. And we can see here that this deployment has been updated to use the same image. But what I wanted to show you here is this replica set is exactly the same replica set that we had when we first deployed our deployment object. So this is how would we get those kind of safety mechanisms with automated rollout and rollback of our application. And we can do the same thing with our SQL application. We can create a deployment object, and that deployment object will have a pod, and that pod will be our SQL application. But we will be missing something, which is how would the ASP.NET pod connect to our database pod? We could start by grabbing the database pod IP and provide it to the ASP.NET pod, maybe through an environment variable. But pods generally are ephemeral, which means they could die for any reason. And if the database pod died, another one will be spinned up automatically, thanks to the replica set. And the new pod will have a new IP. And this is going to break the connectivity between the ASP.NET pod and the database pod. And to avoid this situation, we could use another object in Kubernetes, which is services. And services allows us to logically group a set of pods using a label selector, similar to the one that we used with the replica set. But in addition to that, it also provides us with a DNS name that could be used by the consumers. So in our scenario, we could have a service that is pointing to the database pod using a label selector. And our ASP.NET pod could use the service DNS name to consume that database pod, which means if something went wrong with our database pod for any reason, the ASP.NET pod doesn't have to keep a track of the IPs of the database pod. And this means that our application will be looking like that. We have a service, and the service will be pointing to the ASP.NET pods. The ASP.NET pods will be using the DNS name of the database pod, and that service will keep track of the database pod. And in addition to just being logically grouping the pods and providing us with a DNS name, services also provides us with some sort of load balancing features. So when we put the service in front of the ASP.NET pods, the requests that are coming to our application will be load balancing across the running pods. So let's see how would we update our application to deploy our SQL application, then connect the ASP.NET pod to the database pod. I'm going to clean the deployment. And while we are doing this, let me show you the object definition. So this is the same deployment object that we had in the last demo. The only difference we have here is the environment variable that I have provided. And this is basically the connection string that our ASP.NET pod is going to use. And the key thing that I'd like you to notice here is the name of the server. And this is basically the DNS name of the service that we will build to expose our database pod. And we'll see this in a minute. We can have multiple object definitions inside the same YAML file using those 3 dashes. So this is our deployment object. It's the same one that we have just created. The next one is the service. And again, the same 4 parameters needs to be provided. The kind will be the service, the API version, the name of the service in the metadata, and then our spec definition. And this is the key part here, which is the selector. We could use a different label, by the way. We are using the same label that we have for the replica set, but we could have different labels. The object could have any object could have multiple labels attached to it. Then in this case, we are just using the same label that we have provided in the template definition, which is that one, which is the key app and the value tasks app. Then we have a node port, and there are different types of the service, and the node port allows us to have a random port, and it's static across the nodes of the worker nodes of the cluster, and we can connect to our service from the host using that port, and we'll see this in action. Then the last part of the service is the ports section. Each service could expose multiple services. So if we have multiple containers exposed from the pod, and those containers have different ports, we can use one service with different ports to connect to them. And the ports have 2 parameters. The port that this is the port that the consumers inside the cluster could use to communicate with the service. and the other port, which is the target port, which is the one living inside the pod. The next part is the deployment object of the database. It's similar to the ASP.NET deployment. We have a deployment object with the name MS SQL deployment. The number of replicas in this case will just have one database pod. And then we have the selector, which is, again, using one label, which is app MS SQL. And it's the same label that we have in our template definition for the SQL Server pod. And in the spec section, we have a new parameter that I have provided here, which is termination grace period, which is basically if we decided to delete one of the pods, Kubernetes will allow that pod to be gracefully terminated within 10 seconds. If it didn't die within 10 seconds, it will force killing that pod. And since this is a database, I just decided to give it a few seconds to avoid having any corruption with the data. The next part is the containers and the name of the container. And the image, I'm using a SQL Server image that runs on Linux, and it's actually provided by Microsoft. And again, the image policy that I have here is just to use the image from my local machine. And the port, which is the default SQL Server port. And there are two environment variables that are required by this image, the SA password and accepting the license. So far, we have created the ASP.NET pod, the service sitting in front of the ASP.NET pod, the SQL deployment, and finally, the service that will be sitting in front of the service of the database pod. So it's similar to the one that we have created for the ASP.NET pod. The only difference is the selector and the port that this service is exposing. So let's deploy those 4 objects and see them in action. I'll switch back to the dashboard. We can see that inside the deployment section, we have 2 deployments right now. The first one is for the SQL Server deployment, and inside of it, a replica set, and that replica set is with the pod living inside of it. And as you can see, there is a service already pointing to that replica set, or to the pods living inside the replica set. The new section that I wanted to show you here is the services section, and those are the new services that we have created. And if we open, we have 2 services, the SQL Server service and the ASP.NET service. Opening the ASP.NET service, we can see that they are pointing to the pods living inside our replica set. And if any of those pods died, another one will be created thanks to the replica set, but that new pod will automatically be picked up by the service, so you don't need to keep a track of the new pods. This is done automatically by Kubernetes. So if I just decided to delete or kill that pod, another one will be spinned up automatically, and as you can see, it's automatically picked up by the service. Right now, the other part is the node port part, which is the random port. I think the default range for those ports are 30,000 to 32,700, something like that. And we can use that port to connect to our service from the host machine. So I will grab the tasks app port, and then we'll use local host. There you go. We have the application running. Right now, the only thing that we didn't see so far, which is the manage tasks part, it should be running. But actually, there is one more thing that I didn't do, which is creating the database and the tables that are required by our application inside the database pod. So for the purpose of this demo, I have created a script to do that, which is basically a simple script to create a database and table inside of it. It requires the server name, and I will provide the local host and the port for the database service. Once this is completed, our tasks tab should be running, which is this one. There you go. Right now, we can see that the tasks has been loaded, and we can start adding tasks to it, which is great. All right. The next thing that I wanted to show to you is, so far, we managed to deploy our application, our ASP.NET pod connect to a SQL Server pod, and if the database pod died right now, another one will be spinned up automatically. But the data of our SQL server is living inside the container, which means if the container died for any reason, we will lose the data. And since this is a database, we kind of would like to maintain the data regardless of the pod. And to do this, we need to use another thing inside Kubernetes, which is persistent volumes. And persistent volumes allows us to maintain a set of a piece of durable storage inside the cluster. And it captures the storage details. The Kubernetes cluster has multiple storage options that we can use. It could be either a local storage, a network storage, or it could be even a cloud-based storage. And the persistent volumes have individual life cycle from the pods that could be consuming it. And any persistent volume could be provisioned in two ways. The first one is manually by the administrator, or it could be provisioned dynamically through using another object, which is the persistent volume claim. So the persistent volume claim is basically a request for a persistent volume or a request for a storage. And that request is basically, you could provide, I'd like to request 8 gigs of storage. And there is another parameter that you need to provide, which is the access mode. With the access mode, it's connected to the storage mechanism that you're going to use. And there are multiple access modes. You could have read-write once, read-write many, which determining how many nodes or how many worker nodes could connect and consume your persistent volume. And that persistent volume could be consumed by the pod as a data directory living inside of it. So if we deployed our SQL Server application and as a pod, and that pod requested to have 8 gigs of storage, Kubernetes cluster will automatically provision the persistent volume for us. And once the persistent volume is provisioned, it will automatically connect that volume to our pod to be consumed by the containers living inside the pod. So let's see this in action. I will show you the object definition of creating a persistent volume. I'll clean the current deployment. So here is our persistent volume claim. Again, the same 4 parameters. The kind is persistent volume claim, the API version to be used by the kubectl, the name of the persistent volume claim, the access mode, in this case, read-write once, which means my host, and the resources. And in this case, I just need 8 gigs of storage. And as you can see, I didn't determine or didn't provide the Kubernetes cluster with where that storage will actually be. Is it the host, or is it the network storage, or something? Each Kubernetes cluster have a default storage class or a storage type. And since I'm using my local cluster, the default is using a host path, which is basically a directory on the host machine. You could provide a different host or different storage mechanisms using another parameter, which is called a storage class. Sorry. And you could have different storage class names. And those storage class names determines should I use like Azure storage, or should I use a Google storage, or should I use network storage. But for the purpose of this demo, I'll just keep it simple and we'll use the host path that is living on my host machine, on my local machine. Now that we have the persistent volume claim object, which is the request for a storage, I can consume that storage inside my database pod. So I have a new section here, which is called volumes. And inside the volumes, we have a new volume, which is MS SQLDP. And it's using the persistent volume claim. And all what we need to provide is the claim name. So this is the pod section. So we have added a volume to our pod. Then we can consume that volume inside our container. And we do this using the volume mounts. Inside the volume mounts, we provide the name of the volume and the path, which means if we are like building our, using this volume for our ASP.NET application or any kind of application, this will be the path that your application needs to use to actually write the file into it. And if you are like writing C# application, you can use the normal file IO classes to write to the files to it, such as like stream reader or stream writer. Those will work. You don't have to use a custom or a special APIs to create read-write files inside the container. So let's deploy our object. Before I do this, I'd like to show you the directory that this volume will be created inside of it. And this is basically, since I'm using Docker for desktop, this is going to be inside the Docker volumes directory. So right now it's empty. Once we deploy our object, eventually the persistent volume will be created here, and inside of it, the persistent volume claim. If I switch back to the dashboard, there is a section that allows us to view the persistent volume claims. So we have the persistent volume claim created, and it's attached to a volume. And here is the volume. Also, it's showing me the storage class that I'm using for this persistent volume claim, and this is the default for my local cluster. In addition to that, it's showing me the location of that persistent volume. And if I connect to our application, it's going to work fine. And I'd like to show you, if we went to the database pod, which is our SQL Server pod, we can see that at the last section here that there is a persistent volume claim that is being consumed by that pod. And if I deleted that pod for any random reason that happened, a new pod will be spinned up automatically. And if I open that pod, we can see that it's already attached to the persistent volume claim object that we have created, because we have created, decoupled the storage from the pod lifecycle. And for all the demos that I have been doing, I want to show you that I'm using a Docker for desktop. It's basically, if you are having a Docker installation already on your local machine, you go to the settings section, and in there you have a Kubernetes tab. And once you enable it, this will give you a Kubernetes cluster on your machine. It has some limitations, but it's a very good start to start playing around with Kubernetes and see what are the features and how would you explore with it. But so far, we have been deploying Kubernetes on my local machine. But at a certain point, after you build the application, you would like to deploy that application to a production environment. And you could do this by provisioning Kubernetes in different ways, like on virtual machines on the cloud, or you could use a cloud offering, or even if you have your own data center, you can do this as well. But I usually think that there is a good value of using platform as a service. It might not be the best case for all the situations, but one of the things that I believe in the platform as a service, it makes it very easy to provision a Kubernetes cluster. So we don't need to think about how would we operate and maintain our cluster. As an example, with the cloud offerings from Azure, you don't even need to think what's happening behind the scene for your master node. They are already managing this for us. We don't need to think about how many nodes we need, how would we operate and back up and monitor those nodes. It just happens for us. Moreover, we could also gain some feature like those cloud offerings allows us to update our cluster to the latest version of Kubernetes or change to a previous version of Kubernetes without any downtime of the Kubernetes cluster. We could also scale the number of the worker nodes in our cluster without any downtime. And all those features will take a lot of time from engineering perspective to build ourselves if we will use our own virtual machines. So, and let me show you how would you actually spin up a Kubernetes cluster on top of Azure. It's pretty simple. You just need one command. Azure AKS, this is the Azure CLI. AKS is the Azure Kubernetes service from Azure, which is platform as a service offering. You provide create command and provide the AKS cluster name and the resource group name. And behind the scene, in a few minutes, you will have a fully functioning Kubernetes cluster. There are other parameters that you could provide into your cluster creation as well, but I just kept it simple here, like the number of the worker nodes that you would like to have while you are initiating. By default, I think they are just 3 nodes. After we create the cluster, we need to run another command to access this cluster, which is the get credentials command. And the get credentials command responsibility is to update that kubectl client to point it to the cluster that we just created. And this will allow us to use the exact same commands that we have been using so far, which is actually like a couple of commands, but we don't have to have a different version of the commands while we are connecting to the newly created cluster. So we can use commands like get nodes, or we could apply or create or run. Anything that we do on our local cluster will just work on the new cluster. And with just a simple command, we can spin up or scale the number of the worker node that we have in the cluster. It's just AKS scale. And this will automatically chain the number of the workers that we have in the cluster. Even better, with cloud offerings like Azure, we could have something like Azure Cluster Autoscaler. And when we deploy the Azure Cluster Autoscaler, what happens is it keeps monitoring the work or the pods that are scheduled on the workers. And based on the queue that we have from work on each worker, it could start dynamically provision more worker nodes or kill nodes. And there are some parameters or configurations that we could provide to the auto cluster to determine when to create or to kill nodes. And with this feature, this provides us with a better cost management of our cluster, because we don't even need to worry how many clusters. We don't need to manually keep interrupting our operation and monitoring. We don't have much utilization of that worker node, so let's minimize the workers and stuff like that. And that's basically what I wanted to share with you today. What is the Kubernetes? Why we should care about it? What is the Kubernetes architecture? How would we use the key building blocks of Kubernetes to deploy our application on top of it? And what are the key values of the cloud offering? I'd like to share with you some resources. So I'll publish the presentation later today on my blog. If you would like to see the demos that I have done today, it's already available on GitHub. You can access it right now. If you would like to learn more about the spectrum of Kubernetes, I would like to recommend those two courses, Introduction to Kubernetes and Learn Kubernetes using interactive hands-on. Like with that second part, you don't even need to spin up a cluster on your machine. You can do this in the cloud. And the last part is Kubernetes is moving very, very fast. So if you would like to learn about any subject in Kubernetes, I would recommend to get back to the Kubernetes documentation, because this is the almost always up-to-date source of truth. And that's what I wanted to share with you today. I'm not sure if I have time for questions. Oh, yeah, I think we have time for a question or two. Yeah, go ahead. The mic there.
So using the kube client, when you connect to Azure, it embeds that credential to the kube client. So how do you switch between the local and the
that's a very good question. So the kubectl have something called kubectl config. And with the config, I think I can show it very quickly. So kubectl config. This command has multiple subcommands that you can use. And I will show you ctl config get contexts. This will show me, this will show me the different contexts that I have. So on my machine, I have Docker for desktop, Minikube, and NDC AKS cluster. And I can use a command like kubectl config use context. And the use context will allow me to switch between different clusters. Any other questions? Go ahead.
Could you provide the setup video for the environment you have for this? Just wondering, could you have a video that set up all the environments like your working environment like this, so we can just do some experiment at home in the Windows environments?
So the question is to how would you have multiple environments?
No. Like the Windows environment you set up for the demo today, could you do a video like how to set it up? Like we could experiment how to do it in the Windows environments.
Yeah, this is actually a Windows machine, virtual machine.
Could you do a video like how to set it up, like a step-by-step, what kind of tools to install and kind of.
So first, all what you need is to go to the docker.com, download the Docker latest stable 1. Once you install it, you will have in the settings section, there is a tab for the Kubernetes. And with that tab, you just, this is by default will be disabled like that. Once you enable it and you select Kubernetes, apply, this will automatically configure your local machine with a Kubernetes cluster. It will also configure, I believe, the kubectl to automatically connect to that local cluster. This is not Minikube. This is just Docker for desktop. And it has a feature for the Kubernetes cluster. Go ahead.
just managing your own cluster. I understand there are the cloud options. I've heard a lot of stories of the cluster needing a lot of love to keep it up. What's your take on that? Like, how many people would you dedicate to loving the cluster as opposed to adding value, deploying code?
So yes, having your own cluster, it's similar to have any kind of cluster that you have, but I think there are right now some good solutions that makes it little bit better. So if you would like to spin up your cluster, I think the way to go right now is to use Kubespray, and this will make your life a little bit easier when you are spinning the cluster and if you would like to apply configurations from infrastructure perspective. Go ahead, please.
Yep. So in the demo, you showed that to run the SQL migrations, you use the SQL Service Node Pod to connect directly to the SQL database.
Yep.
Would you still do that in, let's say, a CD pipeline, or would you use, or does Kubernetes offer some kind of objects that allow you to run things within the cluster directly?
Well, I think this will be actually case by case. So I think if you will go with the Kubernetes cluster, the CI pipeline you wouldn't actually use those deployment objects immediately. You would usually go with a Helm chart. So Helm is basically allowing us to have a better management of the Kubernetes objects. So if you have multiple objects, you can package those objects in a Helm chart, and then you would use your Helm chart inside your CI pipeline. But I don't think there is a specific object that I have in mind that comes to the database migration to use with Kubernetes. Does that answer the question?
Yep, thanks.
Go ahead.
Yeah, if you have microservices and you have multiple services deployed and they have to talk to each other, so how easy it is to manage using this Kubernetes?
So I think this is one of the good offerings from Kubernetes. So if you're concerned about the security, there are some plugins that could be attached to the Kubernetes cluster to say this service could communicate to that service or that pod, but it couldn't communicate to the other pod for any reason. From a deployment perspective, I would use different. I would consider each service as its own application. And it should have its own deployment or pipeline, because services should be independently deployed and they should have different life cycle. That's how would you iterate on the microservices. I think that's, I don't have time for more questions, but I'll be here for the rest of the day and tomorrow. So if you have any questions, please feel free to come and chat with me. Thank you.